Have you ever playing video game? Yes, of course. What input device do you use during playing game? What output device do you use? Then, how have you ever know game software communicate with the input or output device? Learning outcomes. At the end of this chapter, students should be able to explain about input-output system organization. Identify direct input-output and memory-mapped input-output and direct memory access. Describe about buffering. Introduction. Humans interact with machines by providing information through input-output devices such as screen displays, printers, keyboards, mouse, etc. Management of all these devices can affect the throughput of a system. For this reason, input-output management also becomes one of the primary responsibilities of an operating system. Input-output manager manages the system's device drivers or works with the virtual memory manager to provide memory-mapped file input-output and manages the file system buffers. Input-output services provided by the OS and how these services appear in application input-output interface. The control of devices connected to the computer is main concern in designing operating system. Why it become major concern in designing operating system? Input-output devices is vary widely in their functions and speed. Varied methods are needed to control them, whereby these methods form the input-output subsystem of kernel, which separates the rest of kernel from the complexities of managing input-output devices. Input-output hardware. Computer operate a great many kinds of devices. It can be categorized into three categories, which are human readable. This device is used to communicate with user, example, printers, video displays, keyboard and mouse. Machine readable. This type of device is used to communicate with electronic equipment such as disk drive, USB, sensors, controllers and PCI bus. Communications. This type of device is used for communication between communication and remotely devices such as network cards, modem, satellite and Wi-Fi. Despite the incredible variety of input-output devices, though we need only a few concepts to understand how devices are attached and how the software control the hardware. Based on the diagram show how each of the devices is being communicate that vary in their signaling method, speed, throughput and connection methods. As in diagram, each of devices have their own controller that control the signals on the wires of a port. All these controllers are attached with the PCI bus that connects the processor and memory subsystem, which are fast devices, and expansion bus that connect relatively slow devices such as keyboard, serial and USB ports. As we playing video game at previous slide, your input device communicate game application via input device driver. The application is being processed and provide the feedback to the output device via output device driver. I/O system organization, detailed. How input-output system has been organized. It being organized into three main area: local peripheral devices, communication devices and storage devices or file system. Logical I/O deals with the device as a logical resource and is not concerned with the details of actually controlling the device. The logical I/O module is concerned with managing general I/O functions in behalf of user process, allowing them to deal with the device in terms of device identifier and simple commands such as open, close, read, write. Device I/O the requested operations and data, buffered characters, records, etc., are converted into appropriate sequences of I/O instructions, channel commands and controller orders, commands. Buffering may be used to improve the efficiency, scheduling and control. The actual queuing and scheduling of I/O operations occur at this level, as well as the control of the operations. Thus, interrupts are handled at this layer and I/O status is collected and reported. This is the layer software that interacts with the I/O module and hence the device hardware. Communication architecture. Logical I/O module is replaced by communication architecture, which may itself consist of a number of layers. An example here is TCP/IP. Directory management at this layer. Symbolic file names are converted to identifiers that either reference the file. This layer is also concerned with user operations that modify the directory of files, add, delete, reorganize, etc. File system. This layer deals with the logical structure of files and with the operations that can be specified by users upon a file: open, close, read, write. Access rights are also managed at this layer. Physical organization. Logical references to files and records must be converted to physical secondary storage addresses, in a similar way as virtual address reference should be converted to physical address through segmentation/paging. During this translation, physical track and sector structure of the secondary storage is taken into account. This layer takes care of allocation of secondary storage space. Input-output system organization. Besides that, the input-output hardware has been organized in two methods: stream-oriented. Stream-oriented device transfers data in and out as a stream of bytes with no block structure. Examples: terminals, printers, communications ports, mouse and other pointing devices and the most other devices. Mode of operation: programmed input-output and interrupt-driven direct input-output. Oriented. Block-oriented device stores information in blocks that are usually of fixed size and transfers are made one block at a time. Reference data is made by block number. Examples: disks and tapes. Input-output communication techniques. Input-output devices operate to interact with user through direct-oriented devices such as a keyboard or an event-generating device, mouse. Usually, user input using a keyboard with a few key depressions at a time, which communication is rarely more than a few bytes. Therefore, this requires an immediate response from the system. Therefore, there are three techniques for input-output communications that includes direct input-output with polling, programmed input-output. The device management software polls the device controller status register to detect completion of the operation. The device management is implemented wholly in the device driver, if interrupts are not used. Interrupt-driven input-output. Interrupts simplify the software's responsibility for detecting operation completion. Device management is implemented through the interaction of a device driver and interrupt routine. Direct memory access is efficient technique when large volumes of data are to be moved. Most network cards are using direct memory access, DMA, mode of input-output with communication infrastructure. Relationship. 3 techniques. From the table we can see the relationship of these 3 techniques of operating system in managing input-output devices. For the input-output to memory via the CPU, it can have 2 techniques which are programmed input-output, which no interrupts is used, whereas interrupt-driven input or output involved interrupt for their operation. However, operations that directly transfer from input-output to memory required interrupt to send signal to CPU once the input-output has been completed. In programmed input-output mode, execution of an input-output instruction ensures that a program shall not advance till it is completed. The program has set of instructions, input-output instructions and computation, and CPU will execute the instructions one by one. CPU encounters an instruction relating to input-output by issuing a command to the appropriated input-output module. Input-output module performs the requested actions. After input-output instruction is invoked, The CPU must determine when the input-output instructions is completed by periodically checks the status of the input-output module, input-output status register, until it finds the operation is complete. The disadvantage: it is a time-consuming process that keeps the processor busy needlessly. The process has to wait for the operation to be completed before proceeding. Example, uses with keyboards. Interrupt-driven input-output. In this mode, CPU issues input-output command to a module and then go on to do some other useful work. Input-output module interrupts the CPU to request services when it is ready to exchange data with CPU. Device controller informs CPU that it has finished its operation by causing interrupt. The occurrence of an event is signaled by an interrupt. Hardware may trigger an interrupt at any time by sending a signal to the CPU. Software may trigger an interrupt by executing a special operations called a system or monitor call. The interrupt transfer control to the ISR, interrupt system handler, through the interrupt vector. For example, for input, the input-output module receives a read command from CPU. Input-output module then proceeds to read data in from an associated peripheral. Once the data are in the module's register, the module signals send interrupt to the CPU. The module then waits until its data are requested by the CPU. CPU is busy checking the module's register, flag, and continues to execute subsequent instruction and interrupted by the input-output module when input-output is finished. Type of interrupt. Polling techniques. The processor checks each device whether if it is a request. This techniques will take CPU time even if no request pending. Vectored interrupt system. Interrupt will cause signal the processor to execute a routine called an interrupt handler to deal with the interrupt. From the diagram show how interrupt-driven input-output operate. 1. E-application process requests a read operation. 2. E-device driver queries the CSR to find out if the device is idle. If busy, then it waits until the device becomes idle. 3. E-driver stores an input command into the controller's command register, thus starting the device. 4. And this part of the device driver completes its work, it saves information regarding the operation it began in the device status table. This table contains an entry for each device in system. The information written into this table contains the return address of the original call and any special parameters for the I/O operation. The CPU, after doing this, can be used by other program. So the device manager invokes the scheduler part of the process manager. It then terminates. 5. E-device completes is the operation and interrupts the CPU, therefore causing an interrupt handler to run. 6. E-interrupt handler determines which device caused the interrupt, it then branches to the device handler for that device. 7. E-device driver retrieves the pending I/O status information from the device status table. 8a, 8b. E-device driver copies the content of the controller's data registers into the user process's space. 9. E-device handler returns the control to the application process, knowing the return address from the device status table. Same sequence, or similar, of operations will be accomplished for an output operation. Interrupt-driven input-output structure. Interrupt-driven input-output structure has two types. If the input-output instruction from the process is non-blocking, it is called input-output synchronous. After input-output starts, control returns to user program only upon input-output completion. If the input-output instructions is blocking, it also known as input-output asynchronous. After input-output starts, control returns to use a program without waiting input-output completion. Direct Memory Access, DMA. DMA is efficient technique when large volumes of data are to be moved. Most network cards are using direct memory access, DMA, mode of I/O with communication infrastructure. The CPU sends a request for the transfer of a block to the DMA module and is interrupted only after the entire block has been transferred. DMA function can be performed by a separate module on the system bus, or it can be incorporated into an I/O module. For example, CPU wishes to read or write a block of data. It issue command O the DMA module by sending to the DMA module the following information which stored in DMA controller, whether a read or write is requested, the address of the I/O device involved, the starting location in memory to read data from or write data to, the number of words to be read or written. In this method, there is no intervention from CPU. DMA module transfers the entire block of data, one word at a time, directly to or from memory without going to the CPU. The CPU can continue with the other work. When the transfer is complete, the DMA module sends an interrupt signal to CPU. The CPU only involved at the beginning and ends of the transfer. DMA is the most preferred mode of communication to support network traffic. Buffering. What is buffer? It is a memory area that stores data while they are transferred between two devices or between a device and an applications. What is buffering? Buffering is a technique by which the device manager can keep slower input-output devices busy during times when a process is not requiring input-output operations. Input buffering is the technique of having the input device read information into the primary memory before the process requests it. Output buffering is the technique of saving information in memory and then writing it to the device while the process continues execution. This technique is used to avoid deadlock. The user memory involved in the input-output operation must be locked in main memory before the input-output request is issued, even though the input-output operation is queued and may not be executed for some time. Buffering. Why use buffer? To cope with a speed mismatch between the producer and consumer of a data stream. Besides, we used a buffer to adapt between devices that have different data transfer sizes, and also to support copy semantics for application of I/O operation. There are two types of buffering. Block-oriented buffering. Store info in blocks that are usually of fixed size, and transfer are made one block at a time. Generally it is possible to reference data by its block number. Example, disks and USB keys. Stream-oriented buffering. A stream-oriented device transfer data in and out as a stream of byte with no block structure. Example, terminals, communication ports, mouse, pointing devices, etc. How buffering can be implemented. What strategies or how this buffering can be implemented. Single buffering. When a user process issues an I/O request, the OS assigns one single buffer in the system portion of main memory to the operation. Input transfers are made to the system buffer. First, the device fills out a buffer. Next, the device driver hands in its control to the kernel to input the data into the buffer. Once the buffer has been used up, the device fills it up again for input. The user process can be processing one block of data while the next block is being read in. Double buffering. It used two system buffers instead of one, whereby process can transfer data to or from one buffer while the OS empties or fills the with other buffer. A process transfers data to or from one buffer whilst the operating system empties or fills to other buffer. The device fills up one of the two buffers, example buffer. The device driver hands in buffer 0 to the kernel to be emptied and the device starts filling up buffer 1 while kernel using up buffer 0. The roles are switched when the buffer 1 is filled up. How buffering can be implemented. Then the third buffering is circular buffer. Several system buffers in the circular queue in circular buffer. The kernel accesses the filled-up buffers in the same sequence as these are filled up. These buffers are filled up in sequence and organized as a circular queue data structure. Summary. As conclusion, the input-output operation has been managed by the operating system either using block-oriented or stream-oriented depending type of devices that being operated during that time. This can be achieved through either using CPU or without CPU intervention such as programmed I/O, interrupt-driven or direct memory access. Other than that, input-output devices used buffering is technique that used when adapting between devices that have different data transfer sizes.